So this is the basic operation of microstrip antennas and basics of circular polarization. Then let us get into the wideband circularly polarized antennas. That means circularly polarized and microstrip antennas. So this is one of my structure that I have done in my work. This These are two configurations I have prepared. One is opposite sides are equal, and uh, one is opposite sides are equal. Here what I'm showing is here A1, A2, A3, A4 are increasing mode. The areas of slot A1, A2, A3, A4 are increasing mode. That is what I'm talking about. Asymmetric nature of the simple square I have taken. In that square, I'm bringing constructional change in order to get two orthogonal modes, right? So the novelty of this particular slot is I have given a circular nature, elliptic nature of the slot in all the four slots. But all the float slots, areas of all the slots are unequal here, asymmetric nature, right? So if you bring that, you're going to get circular polarization. In the next slide, you can see the uh, uh, what do you call the current distribution. If you see the current distribution at 0 degrees, it is horizontal. The field is horizontal, and it is concentrated more on the circular part of the slot. And if you see at 45 degrees, it is rotated towards left hand side. So that means at 45 degrees, lower part of the slot is more concentrated, the current is more concentrated. And then in 90 degrees, it is tending towards left hand side. And 135 degrees, it is completely moved towards left hand side. That means that it is the orientation of the field and rotating in the left hand side. So what we can observe is, so here the important novelty is, so earlier I have seen, I have given you the composition of the slot is triangular semi-elliptic slot. Triangular, I have taken a triangle. Whenever it is flat, actually that analysis also I have done. Whenever the triangular slot is there, the more concentration of more radiation current distribution at that particular slot is less when compared to the circular in nature. So like a high beam light, if you see a car headlamp or torchlight, so there is a concave or convex nature in front of that. That means that the light is going to be scattered onto the wall uh, like like in a conical nature, right? So that is the concept we have taken. I have taken here. Whenever there is a circular a part of that particular slot is there, then the concentration of radiation that current distribution is more. So that because according to that concept, why if it is more, that means that it is going to stay more amount of time. If it is going to stay more amount of time, the phase variation of time phase variation of that particular field is going to be more. That means that you're going to get wider bandwidth and also wider beam width. That is the advantage of this particular sort. That is the novelty of this particular antenna design, right? Next. So this is what I'm talking about. This is we have received around 125 to 145 degrees. Yes.
Sir, Naresh sir,
Yeah.
sorry to disturb you.
Yeah. Yeah.
One participant raised their hand whether to ask any question or.
Yeah. In the end, we can know because
And
there is a
then
lot
that,
of things. Yeah. Yeah.
okay, right, sir. Then. Okay.
Right. Because it is going to disturb the flow, right? Okay.
Okay, right, sir. Sure.
Right. Okay. So there is a wide beam width I've got here. It is not much. There is a 180 degrees wide beam width antennas are also there. But this particular design, I have received only 125 to 145. One particular antenna is received, as I told you, opposite sides are equal. That particular antenna is 125 and another one is 145. I'll show you those things also. Next. So this is, see, first one is all the areas of the slots are different and opposite areas are different in second one, ASP1 and ASP2. I have named it as ASP1 and ASP2, ASP3 and ASP4. ASP3 and ASP4 are scaled down antennas because I've tested for scale down this particular structure to the scale down, because in order to get the higher frequency, whenever f is inversely proportional to lambda, if the lambda is reduced, the frequency is going to be increased, so that the higher frequencies also, this design is going to be, it has been worked, right? Next. This is tested in anechoic chamber. Next. And the results measured and simulated results are like this. And you can see the ASP1 as resonated at 2.4 gigahertz. Another one is ASP2 with opposite slots are equal. A1 is equal to A2 and A3 is equal to A4. For that ASP2, we have got around same 2.4 to 2.5, and scale down versions are radiating at 3.8 to 3.4, in between 3.8 to 4, and another scale down version is radiating at 5 gigahertz. And the corresponding axial ratios are shown in next slide. So I mean, radiation pattern, if you see, there is another thing is the EX and EY, as I talking about, and the two field variations in X direction and Y direction, or horizontal direction and vertical direction, right? So the two planes you're going to get, if you cut in XZ plane and YZ plane of your radiation pattern, so you're going to get two planes. If you match those planes, the difference between those two planes is going to be nothing but axial ratio. But why I'm talking about difference, because it's a log magnitude, right? dB value. So whenever EY by EX is axial ratio, if you take a log value, it is going to be difference. The difference is nothing but axial ratio. So you can find that axial ratio in the next figure. So axial ratios measured and simulated axial ratios are similar, and that itself telling you that it's a circularly polarized antenna. At that two orthogonal modes, that axial ratio should be minimum. So it is around 2.4, near to the 2.4, and another one is at 3.8, and another one is at 4.9 approximately. Right. Next. So these are the gain. Peak gain is around more than 3 dBi, and close to 4 also, 4.2 and 4.3. So I have achieved through this particular design. Next. For all the 4 antennas. So this is comparison with the existing result, and these 4 antennas at that point, this work is published in 2018. So at that point of time, even the gain is not better, but the 10 dB return loss bandwidth when compared to other circularly polarized antennas and dimensions, this is somewhat better when compared to the proposed, I mean, already existing antennas, right? This work is published in radio engineering journal, that is it's an SCI journal, right? Next. So another work that I've done is the similar sort of thing I have taken, but I have taken as slot is different. Here I have taken a trapezoid, and for that I have added semi-elliptic again, because in order to get that particular, as I told you, the concentration of surface current more at that particular point, so that I wanted to get more bandwidth and also the gain, because compromising bandwidth and gain is very important, because there is a big trade-off. Whenever the bandwidth is increasing, gain is reducing. Gain is increasing, bandwidth is reducing. You know that it is a basic thing. So in order to get the compromise in between, so I have done some work on this particular thing. So here also I have done 4 areas, different 4 areas I have taken, and opposite areas are equal, and flat. I mean, as a trapezoid, if you use a trapezoid, it is going to be in the figure B. It's in flat in nature, but at the end of the design, the proposed design is the curvy in nature, so that the curve is going to bring the novelty here, and it is given a sufficient bandwidth in that particular application, right? Next. Next, this is also scaled down to the higher frequencies in order to operate in higher frequencies. Next. Next. So this is measured, and this work is also compared with the existing designs. So this is also good. When compared to the first work, second work, the gain is improved. If you see, the gain is there, it is 3 to 4 dBi, but here the gain is 5 to 5.2 dBi. But in order to, we have compromised here bandwidth. There it is, bandwidth is 200 and 240, 250, but it is 180, 140. This megahertz only, because in this particular antenna, we have taken, I mean, when compared to the other designs, the bandwidth is better, right? Next. This work is complete, I mean, work proposed in, ETRA journal, and the next work is, it's wideband hexagonal triangular fractal antenna. It is a completely wideband antenna. It is It is used for ultra wideband applications. The novelty in this work is it's a fractal in nature. The novel fractal I have proposed here. So I have taken different four hexagonal rings. These hexagonal rings are connected through a triangular patches. Next. So like this, see the composition of antenna. First, I have taken one hexagonal ring, and I have taken second hexagonal ring is connected to the first hexagonal ring through triangular patches across all the edges. And the fractal in nature is iteration one, iteration two, and iteration three. You can observe the composition, right? So what happens is whenever this triangular elements are added, so you can bring down the multiple resonances in order to form a wide bandwidth. You can observe that in the return loss curve, right? Next. So there is a mathematical formula for it, because whenever if you're taking a hexagon, the side of the hexagon is equal to the radius of the center point to the vertex point. The distance of that particular radius of a hexagon is equal to the side of the hexagon. So that is general in nature. By taking that into account, I have proposed this particular antenna. So you can see, I think I've not kept the parametric analysis. If you take iteration 1 and iteration 2 and distribute the iteration 4, iteration 1 is radiating at lower frequency. But iteration 2, iteration 3, if you keep on going towards the final design, the total bandwidth is going to be enhanced. So that figure I have not kept, I think. Let us see. Next. So this antenna is also tested and in anechoic chamber in DLRL laboratory. So next. These are the radiation patterns across the bandwidth, because the antenna is proposed from the gains are taken at 4.2 and 8 and 11 and 15 and 23.5. So huge bandwidth. The wideband fractal antenna has been proposed. Yeah. Next. So the bandwidth ratio is it is 1:8.4 in this particular antenna. Next. So the gain is more at the center frequency, that is around 8 gigahertz, because the antenna dimension is around 20 by 20 So it is here it is 24 by 20 I think. It's very small antenna, so that it is operating at higher frequency. The center frequency is 8, but the gain is also good across the bandwidth from 3.4 to 25 gigahertz. Next. So this is also compared with the existing results, and this work is proposed. Published in IEEE Antennas and Propagation magazine. This is also patented. This particular fractal structure is patented. Next.